So here we want to design an improved low pass filter. In case we're given a low pass filter like this, h of z equals k all over 1 minus a. So this is a general expression for the first order low pass filter. And to get an improved version of this low pass filter, what we'll do is we'll add a 0 to the numerator. So the improved version, so improved low pass filter, so is obtained by adding 1 plus z raised to the power minus 1 to the system. So when we add this to the system, then it will improve the value of the low pass filter. So at this point, we'll now put that here. H of z will now be equal to k into 1 plus z inverse all over 1 minus a. 1 minus a z inverse. So as this one is, we are going to convert it to the Fourier transform version of this. This is the Z transform version. So we are going to convert it to the Fourier transform version by replacing Z. So you just to do that, you just need to let Z equals to e raised to power j omega. So by doing that, so this is going to be that's going to be h omega. It will now become 1 plus z inverse all over 1 minus a z inverse. It will be equal to, or let's say this is going to be e raised to power minus j omega, and this is going to be e raised to power it's going to be e raised to power minus j omega. So as this one is now, it is in the Fourier transform version right now. So what we do at this point is that we are going to get the value of this h omega, this response. We need to get it at omega equals to 0. So that's the general expression to get the value of k, because we need to get a value for k. So to get a value for k, you now set omega to be equal to 0, and at omega is equals to 0, h of 0 is equals to 1. So at this point in time, when we substitute this into this equation, h of 0, so that will be k into 1 plus, so e raised to power minus j omega, that will be e raised to power 0, then 1 minus a e raised to power 0, and now e raised to power 0 is 1, so this will become 1 plus 1, 2k all over 1 minus a, and that will be equal to 1. So from this we will know that the value of k here is equal to 1 minus a all over 2. So if we now put k back into this initial equation of the low pass filter, so it's going to be h of z is going to be 1 minus a all over 2 and 2. So 1 plus z inverse 1 minus a z inverse. So this is the general expression for the low pass filter. And at this point, a is in this range, is within 0 and 1. Okay, so we now want to get h of z. So once we get the magnitude of h of z, so of h of omega rather. So if we convert this one to the Fourier transform version, we have h omega is going to be 1 minus a all over 2 1 plus e raised to power minus j omega. Then this is 1 minus a e raised to power minus j omega, right? So this e raised to power j omega can be converted to the rectangular form of complex numbers. So let's convert that. So this is going to be 1 minus a all over 2, and that will be 1 plus, this is going to be cos omega plus j sine omega all over 1 minus, so a cos omega, then this is going to be minus the minus that is coming from the expansion of the bracket with the minus that is coming from the power. So it's going to be plus sine a sine omega. So this is going to be the expansion. Now as this one is now, we now want to put the real and the imaginary parts aside and find the magnitude. So this is h omega right now. This is h omega. So we now want to get the magnitude of h omega, the magnitude square, the square of the magnitude. So the square of the magnitude, h omega square, is going to be square of this one as well. This is 1 minus a all over 2 squared, and when you square this one, this is going to be, the real part is 1 plus cos omega. So that real parts, now we bring them together, we square them, to find the square of complex number. You multiply them, you multiply the real part and the imaginary part, that is, you find the complex conjugates and square them together. So that's how this one is going to be obtained. So sine omega, this one will also be squared. So the real part and the imaginary part, if you look at this very well, the complex conjugate is what is being squared. So when you square, you take the real part, you square it, you take the imaginary part, you square it. So and that's it's just like you're doing difference of 2 squared. So like the same thing with the denominator. So it's going to be 1 minus a cos omega over squared, then plus also it's going to be a sine omega square. So we will now expand this particular expression. So we expand it. So it's going to be 1 minus a all over 2 square, and this is going to be 1 plus 2 cos omega, then plus cos squared omega, then plus sine squared omega, all over, it's going to be 1 minus 2a cos omega plus a squared cos squared omega plus a squared sine squared omega. So now that we have this, the next thing we want to look at is we see that cos squared omega and sine squared omega is going to give us 1. So let's take that one to be 1 and put that into this expression. We have 1 minus a all over 2 squared, and this is going to be 1 plus 2 cos omega plus 1, and this is going to be 1 minus 2a cos omega plus, so a square will come out, so this is going to be cos square theta plus sine square theta, which is 1. So what we left there is a squared. So that's the expression here. Now with this expression obtained like this, so we say that 1 plus 1 at the numerator will become 2, and that's going to be 1 minus a all over 2 squared, then this is going to be 2 plus 2 cos omega, then this is going to be 1 plus a squared minus 2a cos omega. So, and this is going to be, we can now extract the 2 out. So this is going to be 1 minus a all over 2 squared. 2 is coming out of this, 1 plus cos omega, and this is going to be 1 plus a squared minus 2a cos omega. And when these two cos this 2 at this point, you still have another 2 left there. So this is going to be it's going to be 1 minus a squared all over 4, and this is 2 here. So when these two cos that 4, you are going to be left with 2 at the denominator. So you have 2 here, and this is going to be 1 plus cos omega, and this is going to be 1 plus a squared minus 2a cos omega. Now this one as it is obtained now, we want to look for the 3 dB cutoff frequency, and that one is obtained by setting this omega h omega square, by setting it to equal to half. So at 3 dB cutoff frequency, so at 3 dB cutoff frequency, so h omega square is equals to 1 over 2. So that's what we are going to set this equal to. So at that point, when we set this equal to that, we are going to have 1 minus a all squared, then 1 plus cos omega all over 2 into 1 plus a squared minus 2a cos omega, and so that will be equal to 1 over 2. So these two will cut this 2 here, and when we cross multiply, we're going to have, so when we cross multiply, we are going to have 1 minus a squared 1 plus cos omega will be equal to 1 plus a squared minus 2a cos omega. Now as this one is now, we see that we want to make cos omega the subject of the formula. So at this point, we know that cos omega is inside this bracket, so we can expand the brackets. We expand the brackets, and this is going to be 1 minus a squared 1 minus a all squared, then plus 1 minus a whole squared again cos omega will be equal to 1 plus a squared minus 2a cos omega. So let us bring the cos omega term. Let's bring them together. So this is going to be 1 minus a all squared cos omega plus 2a cos omega. So we have 1. If this one goes to the other side, you have 1 minus a squared, okay, plus a squared is also here. Okay, so here now, if we bring out the cos omega, bring them out, so this is going to be cos omega by 1 minus a squared plus 2a, right? So 1 minus a squared plus 2a, and on the other side we have 1 plus a squared minus, if you expand this, we're going to get 1 minus 2a plus a squared, right? So this cos omega from here is equal to 1 plus a squared minus 1 plus 2a minus a squared all over, the denominator is 1 minus 2a, right, plus a squared once it is expanded. Okay, so this is now going to be, so at this point you see that this can cut this, and that this one will also cut this, so then 1 will also cut minus 1. So at the numerator you are left with, at the numerator we are left with 2a. That means cos omega is equal to 2a all over 1 plus a squared, 1 plus a squared. So that's cos omega. So this is one version in case we are looking for the value of omega. So it's called the central frequency, the cutoff frequency. So that's why it is called omega c. So omega c can be obtained from this one like this. So also we can also look for the value of a given omega c. In case we are given omega c, I will want to look for the value of a. What will be the value of a from here? So that will be obtained by making a the subject of the formula. And to make a the subject of the formula, so what we'll do is we just you can rearrange this particular equation so that this is going to be 1 plus a squared when you cross multiply cos omega is equals to 2a. So that means a squared cos omega plus cos omega will be equal to 2a. So if 2a comes here, we have a squared cos omega minus 2a minus 2a plus cos omega, which will be equal to 0. So looking at this expression, if you consider a to be the variable in this equation, you see that it's a quadratic equation that we need to solve for a. And using our quadratic formula, we can guess the value of a. So let's use our quadratic formula to determine the value of a. So a from here, so we just take our a to be, so in our quadratic formula, if this one is our formula is a is going to be minus b plus or minus b squared all over 4ac, right? So the first term here, so is going to be the a. So that's going to be a is going to be minus the middle term, which is minus 2. So that's minus 2. Then plus or minus, then b squared, which means the middle term square. So that will be minus 2 squared, right? Minus 4ac. So 4, then a is a, that is the first term, the coefficient of the first term, which is cos omega, and c, which is the coefficient of the last term, which is cos omega as well. So all over 2a, which is coefficient of the first term, which is cos omega. So if we now solve this expression, this equation, now we know we have obtained the value of a from here. So this is going to be 2 plus or minus square root of 2 is 4, then 4 cos square theta, cos squared omega all over 2 cos omega. So from here now we'll just simplify further. This is going to be 2 plus or minus. So if you take 4 here, and this is going to be 1 minus cos squared theta, cos squared omega, and that's going to be 2 cos omega. So that will be 2 plus or minus square root of 4, that will be 2, and then this is 1 minus sine squared theta, 1 minus cos squared theta, which is going to be sine squared theta, and square root of sine squared theta is going to be what? Sine theta. So that means it's going to be sine omega eventually, and this is going to be 2 cos omega. So if these two, if they cut, you're going to be left with a will now be equal to 1 plus or minus sine omega all over cos omega. So this is the value of a. So that's the value of a. So since this value of a has two versions, so we are going to choose the one that will make the system stable, and the one we are going to choose is going to be 1 minus sine omega, but that's what will make the system stable. So the value of eta will make this system stable, because if you choose 1 plus sine omega, an increase in the value of omega, it will not make this thing converge. So for it to converge, you need to choose 1 minus sine omega. So, and that is going to make the system converge. So what's reasonable here is that a is equal to 1 minus sine omega 1 all over cos omega. So that's the one we are going to choose for this system. So this is the solution for the filter, for the low pass filter. So these values, so we have been able to determine the low pass filter equation with this. So that's it.